Hello. I would like to start by thanking the organizers for inviting me to present some stuff here during this webinar. And I will talk about online personal AIQ. What did it change? Okay, I will talk about personal AIQ monitoring, and what I call AIQ will be indoor air pollutants. I would focus more on indoor air pollutants and on personal exposure. So all the work I will present here will be probably a bit less technical than the previous speaker, and it's just some examples of what we did within the Apolline network of the University of Lille, the air pollution and individual exposure, which aims to develop a network of small size, low cost pollutant monitoring system for monitoring indoor and outdoor environments. And we are deploying this network on the campus, but also in other environments, with the objectives of understanding the drivers of the dynamics of pollution inside buildings, which is one of the main issues still in indoor environments. We do not know at all everything we should know about what is driving the pollution inside the buildings. And second research objective is to quantify the exposure of people, that is the health effects. And hey, why is it moving? And this is not only a research project, it's also for education and awareness. And okay, so the strategies we developed to monitor this personal exposure starts by this question is, where do we spend our time? And as we can see here on this graph, is on the blue side is indoor in the home. Red should not be. Red is outdoor, yellow is at work, and this is other indoor outdoor location and transportation, and there were bars, restaurants, and other public facilities. But most of it is we spend our time mostly indoors and mostly at home. So we have two strategies to get the exposure of people. First one is we get personal sensors. And what we mean by personal sensors is wearable sensors. So you take people and you give them sensors, and then you measure continuously, but then you have to get some size and weight and autonomy and communications, and some technical issues of how to prepare the object, connected object or critical. Of course, because of these constraints about size and weight and autonomy, you cannot put all the sensors you would want inside the device. But there is a really big advantage of this, is that you have at the same time access to the indoor exposure and to the outdoor exposure. And I will say a bit more about this now. And then there is the second strategy is, okay, you just consider the environment, the indoor environment, for instance, and you put some fixed sensors in there, as was presented, for instance, by the previous speaker. So you have less constraints on the technique. You have less technical constraints, of course, but you have access only to the room or the building concentration, which is not exactly the same as the exposure of people. Then you have to consider also when the people are in that room or in that building. So this is just to show you how we get from sensors to data. So we just get individual sensors monitoring the pollutants or the physical parameters that we want to do. So like CO2, NOx, VOCs, particles, temperature, humidity. We just assemble either in personal wearable sensors or in fixed sensors. And then, okay, you need to send all the data to some storage infrastructure where you can at least, and that's the list we do, we just display on site or for some mobile application when using personal sensors. And okay, if we use the wearable sensor strategies to just take the people, so we need first lots of people. Is the only way to work with that is to work in the field of citizen science. And so we need many volunteers. to explore different environments and to check the variability between people, between environments that the people go to. So it would be nice to have sensors on many people, but of course that gives some logistics problem, that gives some cost. Low-cost sensors are low cost, but if you start multiplying the number of sensors, then it's just not that low cost anyway. So a few examples here is like 24 hours in the day of I don't know who. And as you can see, from midnight to midnight next day, so people were at home with high concentration here of particles, which were discussed and attributed to other people, like ventilation system, which was not quite clean actually, and giving concentration up to 1,000 microgram. Red line here is the recommended alert value of 80 microgram per cubic meter in outdoor air. Indoor air was much worse. During daytime, I don't know what people were doing, which was just some random blind citizen science experiments. Okay, but there were some points also outdoors where concentrations were not that high. Okay, so one of the questions or challenges that we have to face when using this kind of approach is, well, where do you know where we are? Is how to discriminate the indoor and the outdoor. So we can look for jumps in temperature, humidity, number of satellites that are seen by the sensors. Another challenge, and the previous speaker also mentioned a bit about this, is the metrology of sensors and the quality of the data and the quality of the measurement. Also technical challenges, the data transfer, the autonomy, and then there are some challenges which are more science related, is the time and space variability, which is one of the question that we would like to answer, the inter-individual variability. So this is not only the place, but it's also the behavior and the activity of people. And also, are the sensor people proof? This might sound like a funny question, but this is really a requisite that sensors could be people proof and that people cannot interfere with the sensors when they wear them. Because it will, of course, add to problems of the quality of data and problem of the representativeness of the data and information that you try to get out of the experiment. I will switch this example, which is just measurement taken in the subway in Lille and with much higher concentration than outdoor and indoor. So we consider also not only buildings, but we consider every kind of indoor environments in transplantation, for instance. Okay, if we look now at the second strategy with the fixed sensor strategies. Okay, in a room, in a building, we have different rooms with different activities. So different kind of pollution, different levels of pollution. So we will not be looking at the same kind of compounds or the same concentrations in a kitchen, in a garage, in a living room, or in a bedroom. Okay, so we in some way could wish to put sensors and sensor nodes everywhere, but that would get very expensive. And would that give us all the information we would want? Is, well, maybe not. And here is one of the questions is, are all these environments and all these buildings and all these houses and all these rooms in the buildings really different? We have been doing experiments in the last 2-3 years about this, and I present here 6 different buildings, 7 different buildings here. And if we just look at different parameters, temperature, humidity, or CO2, nitrogen oxide, and particles, actually most of the measurements fall into the same range, which means that basically the level of concentrations and the environments behave quite similarly most of the time. And when we have this statistical outliers, actually these correspond to pollution events or specific pollution events, which are more related to activities inside the room or inside the building. And so we can distinguish at the same time between normal levels, I wouldn't say healthy levels, and activities and abnormal levels or pollution episodes. So, which is a good thing that all the buildings behave similarly, which means we don't need to put sensors everywhere. So that will reduce the cost and that will reduce also the amount of data that we need to collect. And if we just look at one of the traces in one of these experiments, and here is same experiment for CO and same time for particles, PM 2.5, and we were asking the volunteer where the sensor box was installed to tell us what it was doing at the time, from cooking or from using other chemicals or doing other activities. And so there was self-reported activities, some which cover more or less every time we see an event, a pollution event, there was some activity associated with it. Not all the time. So sometimes there are other activities that we don't know what it is. But then what was important in here is that we could, from this trace and from this log of activities, construct some chemical signature of the activities. And this is important because that means that all these outliers in this previous slide in the comparison actually means something, and we could more or less recognize an event by its chemical signature. So, which is of course interesting when we want to apply automatic detection and automatic analysis, but we still need to construct such a large database for such signatures. We did not investigate all kinds of events, and also we did not investigate all kinds of behaviors or activities. So we need to build up such a kind of database progressively. Of course, we had some obvious experiments measuring also CO2 at the same time. And CO2, if we take here in dashed red, the 1000 ppm level usually used, which is more like 1500 ppm in France, we could see just a simple experiment of students in their office in the lab, and with the concentration of CO2 increasing when they're here working, we hope. And of course, this is typically what is used or should be used as for CO2 as a trigger for the ventilation. And this could be useful. CO2 is not the only proxy that could be used. Could be used particles, but it's usually harder to measure and less sensitive. CO2 is definitely the best for that. So now, all I've said before was just about measuring or visualizing data. And if we want to get to the next step, it's just not the data, but it's information that we need. And for information, okay, we have the sensing nodes, we have the data measurement with the quality problem of data. We send all the data on the server, okay, and then, okay, we have to analyze the data. And analyze the data for people in chemistry, analyzing such an amount of data with sometimes acquisition frequencies of a minute with tens or sensors inside one box and tens of boxes around, gives us a really data tsunami that we do not know yet how to really analyze and how to exploit. Because, okay, in some ways, we know what we are looking for. For instance, if we're looking for healthy levels, or if we're looking for exposure, and if then, okay, we just look at time series, we know more or less to do. If we want to look on the previous example at a pollution episode linked to activities, well, we don't know exactly yet, at least for us in my group, we don't know yet how to look for this data. And that is one of the questions, and that is mainly the focus of the ongoing work, is how to analyze all this data. And that is either from the data that's been collected on the server, but we have also another question that we are trying to address is, well, do we really need to analyze all this data? And do we really need all the data that are measured? And do we really need to analyze all the data once they are on the server, or can we do it directly on the sensing node? And that would have some good side and some bad side. And the bad side is, if we work only on the sensing node, and we can apply even some machine learning activity processes directly on some small micro chip inside the nodes, but we have only partial information. We have only the information from the sensors. Okay, so we don't have access to other metadata like outdoor air or activities or logs. Or so of course there would be a problem of computational power available inside the box, which might be limiting. But on the good side, there would be less transmission of data. Raw data are not information. So if you want to transform it, maybe it's easier to just work with onboard computation. And probably that would be also more energy efficient because that would be less transmission just by restricting the transmissions of data or of information to the useful, to the meaningful information that has been derived from the data. So this is something that has to be considered when we put sensors everywhere, or when we want to get information, and when we consider Internet of Things and connected objects. Is, okay, multiplying the objects is good, okay, but is it really energy efficient? That is the goal of the Annex 86, to check for energy efficient buildings. But if we had a system that is not that energy efficient, what are we working in the right direction? And this is one of the questions that needs to be addressed in the future. But of course, for testing and for developing all the processes, it's just better or easier to work first to develop all the processes from the server, data on the server, and then to try to apply them as much as we could directly on the sensing nodes. So I would finish with, I hope I'm still on time, I would finish with, okay, wearable or fixed sensors allow really now to monitor or evaluate the personal exposure to pollutants inside buildings and more generally inside closed environments. And they are related, indoor air is related to outdoor air. And so we need, if we want to understand really the drivers of the pollution patterns inside indoor environments, we also need outdoor. But then this is true only if you can fix all the technical issues about the sensors response and the quality of data, about the size and weight, autonomy, cost, communication, infrastructures, and everything, which are technical object related issues, which are not obvious. If for environmental parameters like temperature, humidity, we can more or less trust the response of the sensors, this is definitely not the case yet for chemical pollutants, gases or particles. And so the metrology of sensors definitely, and the quality of the data definitely needs to be addressed first. Second issue, third message, okay, low-cost sensors are not that low cost if you consider the infrastructure, the calibration and issues, and the environmental cost, the lifetime of the sensors, the operation, the calibration, and the communications. So that is not so low cost as we would wish. For exposure problems, or we would recommend working jointly with a network of wearable sensors, following individuals wearing sensors, fixed sensors where we can inside buildings, reference monitoring stations outdoor. So we would recommend working with all the data that are related to pollution. But then, once again, there are questions that we need to address before developing such a network is, okay, what do we want to do with all those sensors? What do we want to do with all those objects? Do we want to work on exposure characterization, which was the title of my talk initially, and which was actually the initial goal also of the project? Do we want to focus on the pollution from the building? Do we want to focus on the pollution from the activities? Do we want to get some building management system? Do we want alerting system? Okay, and this is not always clearly defined in every system that I've seen so far, even in my lab or in other systems that have been reported in conferences or in papers. This is not always really sufficiently defined, and this leads to sometimes people getting off track because, well, they did not clearly clarify what they want to do. What are we looking for? Are we looking for environmental parameters, temperature, humidities? Where are we looking for particles, for gases? Do we need the speciation of the gases? Are we looking for some exposure, integrated exposure? Are we looking for pre-identified events, for unexpected events? So this is more about what kind of sensors we should use and how we should analyze. So how we should analyze is several questions need to be addressed. Do we need for research, probably delayed analysis after we have been acquiring the data? Sometimes it's fine. Do we need real-time analysis? If we want alerting system, that would be yes. Do we want server or onboard sensor analysis? Do we want just merely time series classification, artificial intelligence? So what do we need to analyze all those data, all this really tsunami of data? I do not know yet, and I will learn in the previous presentation and in the next presentation. I hope I will learn things, how to do it. This is clearly mainly for pollution sensors, uncharted territory yet. So these are some of the questions that we will try to address in the subtask 5 of the Annex 86. Mauro Delgos told that already in the introduction. So thank you for your attention, and I will thank all the participants in the studies and all the funders and the organizers. Thank you.